Well, today we'll continue talking about differential equations. Last time we learned how to solve a few of them. A very important form because it occurs in lots of mathematical models is called normal form for a first order differential equation. If you're looking for an unknown function y of t an independent variable, y a dependent variable, and you're given this equation that it has to satisfy. So you know what function f is. dy dt equals some function of f in ty. Say, I wonder what function y of t satisfies that equation. Well, this is called normal form. If dy dt is all by itself on one side equals a function of just t and y on the other. And in this case, we can actually do the following. Suppose we can't solve the differential equation. We can often get a qualitative analysis of it, a rough sketch of what do the solutions kind of look like in the plane, in the ty plane. So to do that, what we'll do is assign a line segment of slope f of ty to each point ty in the plane. And we know that since solutions to this equation, y of t have to satisfy their slope equals f of ty, the slope of the line segment will be equal to the slope of the solution that goes through that point. For instance, down below, I have a worked out example here. Suppose I want to find the direction field of all line segments. In your book they call it a slope field. It's less common. Most books call it a direction field. And in this big region here, the ty plane, all these little red line segments like this are the slope field, the direction field. And if the differential equation is y prime equals y minus t squared, you say, what function y of t satisfies this equation? Well, you can do the following. At the point 0, 0, you have 0 minus 0 squared. Y prime has to equal 0. So when you're at 0, 0, right here, the slope has to be 0. You draw a little horizontal line. If you're at the point 1, 1, 1 minus 1 is 0, so y prime has to be 0 there. I go to 1, 1, and under here there'd be a little horizontal slope also at the point 0, 1. So 1 minus 0 squared, the slope has to be 1. So I go to 0, 1, and right here, you draw a line segment of slope 1. And if you fill up the plane, you see this is very tedious in practice. You fill up the plane, here's some line segments that are slope 0 at this point. Here's line segments about slope 1 or something. Here's some line segments of about slope minus 1. And you fill up the plane with all those little line segments, you begin to realize that solutions to the differential equation, just by virtue of the equation, they have to have slope equal the slope of the line segment you drew. So you draw these are solution curves. Why? They have to pass through the plane being tangent to every horizontal line segment you drew in the direction field. So this one goes down like this. It has to be tangent to this line segment, tangent to this line segment, tangent to this one, tangent to this one. You can kind of see it. It's like flowing water, and your little boat you put in the water floats along that direction field, just tangent to all the streamlines there that you see. And here's another solution. Remember, a differential equation in general has an infinite number of solutions, one for each arbitrary constant you get from the integration you do solving it. And so there's an infinite number of these solution curves to the differential equation we can draw. And then if we also apply that initial condition and say, well, at t equals t0, y equals some number y0, then that picks off one of these. For instance, if I also said when t equals 0, y has to equal 0, then that means I have to go through the point 0, 0 right here. And it would be a solution right about here. And we could draw it like this. The solution that had that initial value would look about like that, something like similar to this curve, but moved down a little. So there's an infinite number of solutions. If you apply an additional initial value, it picks off one of them. And so each of these represents a solution corresponding to an initial value. Like this one looks like it goes roughly through 0 minus 1. Y of 0 equals minus 1 would be an initial condition that says you have this is your solution to that initial value problem, the differential equation with that initial value. Alright, so the object here is when you get a differential equation, maybe you can't find the solutions, you can still get an idea how they move by drawing this direction field and trying to make curves that are tangent to each line segment in it. Well, there's some nice examples in the book also. Let me look at one. Here's out of a homework set. Suppose I wanted to find the slope field for y prime equals xy over 4 at the 25 grid points where x goes from -2 to 2 and y goes from -2 to 2. I could sketch all those little line segments, and then I could try and draw solutions that pass through that slope field and are tangent to each of the little line segments in it. So here's that one. I go from -2 to 2 on both axes. And I'm trying to solve dy dt of dy dx equals xy over 4. Find some solutions to that by approximate drawing, a qualitative analysis instead of actually finding the solutions. Well, what you do is you go to each of the points, and you can make a table here. Here's x, y, and here's the slope, xy over 4. So at the point 0, 0, I get slope 0. Right here I draw this little direction field segment. And then at the point 1, 0, I get 1 times 0 over 4, it's still 0. And at 2, 0, it's 2 times 0 over 4. And there's a bunch of other points here that we can plot similarly. We begin to realize that whenever x is 0, xy over 4 will be 0, so we have these direction field segments. And then also, if I put in some points where y is equal to 0, I put like 0, 1. Well, 0 times 1 times 0 over 4 is 0, so it's 0. In fact, whenever either x or y is 0, we're going to get slope field 0. So we draw in these little segments. And now we can draw some other points, like 1, 1. At 1, 1, we get 1 times 1 over 4. The slope has to be 1/4. So at this point right here, I draw a little slope of 1/4. Let's look at the the point 1, 2. Now we got 1 times 2 over 4, it's a half. So at the point 1, 2, the slope's a little bigger. And at 2, 1, I notice also 2 times 1 over 4 is a half. So 2, 1, let's see, that was 2, 1 I drew, wasn't it? 1, 2, I have a slope 1/2, about like that. And at the point 2, 2, I'm getting the biggest slope. 2 times 2 over 4 is 1. So way up here, I have a slope 1. And then you can put over here, when x equals -2 and y equals -2, it's also 1. And you get sort of a corresponding picture here. This is still slope 1/2, right? At -1, -1, you get -1 times -1 over 4 is 1/4. And this one is also 1/2. And so you get this symmetry in the field. You can sometimes apply that to your advantage. Let's try the point 1, -1 at 1 and -1, I get -1/4. At -2, 1, I get -2 times 1 over 4 is -1/2. So now it looks more like this. Let's see, at -1, 2, I get -1/2. About like that. And now we can kind of figure how these things look. We got a similar situation over here if we draw it in. Let's see, this is -1/4, wasn't it? And this one is also -1/4, and -1/2, -1/2, and -1. Now we can try and draw solution curves through there. Solutions ought to look kind of like this. And they pass through here. They have slope -1 and then slope -1/4 here. They might pass through here and then come back up. Solutions down here. Just think of this as flowing water. Look like a flow cut out like that. There's one solution here that just has slope 0 all along the way. And so we might fill up the plane with approximate solution curve like that. Okay, now how about this one? A slope field for the differential equation y prime equals 1 minus y is shown in the accompanying figure. In each part, sketch the graph of the solution that satisfies the initial condition. Suppose when t equals 0, y is -1. That's what it says. So let's see. Here's. Gotta go find this now. Yeah, sorry. Yeah, it's this one right here, I'm sorry. If you want to sketch the graph of the solution, it has to go through tangent to each of these. So some of the solutions are coming down like this. It can't pass through this line because this is a solution itself. Some of the solutions are coming up like this. So this is what the solutions look like given this direction field. You can sketch the solutions to be approximately tangent to each little line segment. Excuse me, and here's a solution right through here. Y of 0 equals -1 means it has to pass through the point t equals 0, y equals -1, so it's right here. We want the curve that goes through that point, so we just, the differential equation together with this initial value, there's only one solution and it goes like this. If you wanted to sketch it. How about y of 0 equals 1? Now it goes through the point 0, 1. That's this solution, right? Y of 0 equals 2. Now it goes to the point 0, 2, so it must be a solution that looks like that. Now these solutions, it turns out, can't cross. There's an existence uniqueness theorem. You got 4 nice differential equations. This is a nice one. It has an easy function on the right-hand side. What you need is discontinuous and its partial derivative that I haven't talked about with respect to y continuous. And they are. So you, in that case, the solutions can't intersect. There's a solution here. That means this solution up here can only come closer and closer. It can't actually intersect it. So keep that in mind when you draw the solutions. They can't cross for nice differential equations like this. All right, well, let's carry this a little further. Sometimes these direction fields are very difficult to draw, as in this case. Suppose I want to sketch the direction field for dy dt equals y minus t squared. Not so terrifically easy, right? And use it to sketch the approximate solution curves. Well, you could be all day drawing all these little line segments. I'll let a computer draw those. One of the points here actually is that there are computer programs like MATLAB where they have built-in software that will sketch these direction fields very nicely for you. And you don't have to go to quite so much work, but you still want to have a feel for how to do this. So for this section, you are the computer, have to draw these little line sections. But what you can do to make your life easier when you have a lot of these to draw is draw what's called isoclines. I don't think these are mentioned in the text. But an isocline is a curve in the xy plane along which every direction field segment has the same slope. Like for instance, and so here, if I want to get a particular slope, I take a curve y minus t squared equals a constant. If I take y minus t squared equals 0, I say, oh, that's the parabola, right? Y equals t squared. That's very easy. Let's see, it's this one right here. Y equals t squared that goes through 0, 0. And along this curve, y minus t squared equals 0, If this is 0, dy dt, and the solutions have to be 0, every line segment that goes through this curve right here will have slope 0. So I draw y equals t squared just with little dotted lines, and then I draw a whole bunch of direction field segments all at once. Now I try y minus t squared equals a fourth. Everything that goes through that parabola, y equals t squared plus a fourth, it's one like this one here, I suppose. Every line segment I have to draw there for the direction field has slope 1/4. Now you see how you can get a whole lot of these direction field segments quickly. You draw the isoclines dotted, and then along every isocline you just draw line segments of the same slope. Y minus t squared equals minus a fourth. So I draw that parabola, y equals t squared minus a fourth. That's maybe this one. And on this one, it's probably this one. On this one, every line segment I draw in there has slope minus a fourth. Now you can fill up the plane with a lot of those. And then these are the solution curves. You try and draw these tangent to every direction field segment. So you have tangent there, and then tangent there, and then tangent there. This one is tangent here, and then tangent here horizontally. Goes up a little, then it's tangent horizontally again. Starts to follow these direction field segments downward. So there's how you can draw direction field segments. Is whenever you have a differential equation in normal, of first order, meaning first derivative is the highest. In normal form, meaning dy dt equals the function of t and y alone, you can draw a direction field by taking the right-hand side equal a constant to get the isoclines and make little line segments of the same slope, whatever that constant is. And then draw solutions, try to be tangent to all those direction fields. If you have an initial value, you pick the solution curve that goes to that particular point picked off by the initial value. Okay, so that's all I want to say on slope fields. Now, let's go over to this section. This is my own notes, not in the book. What happens if you get a really bad differential equation that you can't draw a direction field for, or you want to actually find a real close approximate solution, not just a rough sketch of the curve. You want to get a pretty approximate solution, but you can't solve the differential equation. You can't find the actual function y that satisfies dy dt equals f of ty. Together with an initial value, y of t0 equals y0. If you have this initial value problem of a differential equation with an initial condition, you can use what's called Eulers method. It's a very simple method. There's much better methods you can take in numerical methods class. But this is a beginning method for solving these. It's pretty easy to program. Suppose, well, we derive the method as follows. Suppose we have, we break an interval on which we want the solution estimated from t0 to tn, from a to b, with t0 equal a and tn equal b. And on each interval, we just take a little step to estimate the solution at the next point. Here's what Eulers' method does. Here's a whole bunch of solution curves, sometimes called integral curves for these, for this particular equation. Solution curves. And if you're starting with some initial value, t0, y0 here, you could say that approximately the solution is tangent, follows the tangent line to it. If I take this tangent line, it almost lands on the next point in the solution. So this blue line is the solution you want. It's the solution of the differential equation that goes through your initial value here. But if you just take a tangent line and go to here instead, you're almost on the solution. Now you're on some other solution. You take a tangent line to n and go to another point. You're a little further from the solution usually, but undaunted, you take a tangent line to the solution that goes through this point, and you come to here, and if you keep taking the tangent to each of these different solution curves, you tend to stay not too far from the solution you wanted that goes through the initial value. That's Eulers' method. It takes a tangent line to each of the solution curves it encounters. By this method, it takes yn plus 1 equals y at the nth step, plus the book puts delta xn times f of tn yn. So hn is what's used in a lot of numerical analysis books, but whichever one. Yn plus 1 equals yn plus hn f of tn yn gets you the y value at the next point on this sequence of points given yn, the value of y at the current point. So Eulers' method doesn't give you a function, it gives you a bunch of points. It gives you this point, this point, this point, this point, and this point, estimating these points in the actual solution. And so this is a numerical method, a number crunching method to estimate points on the solution curve by this algorithm. So here's one step of Eulers' method. Here's the actual solution curve. You instead take the tangent line and go to this point and say, tn plus 1, yn plus 1 is approximately a solution of the curve. When I take a step aside hn or delta tn, the book would call it, I go up this high, estimating this point on the curve. So there's Eulers' one-step thing. Here's the actual algorithm. Given a point t0, y0, a beginning point, and you're going to go through n steps with hn, the step size at each point. Usually we pick the same step size at each point. We'll start with t0 equal t naught, the initial point that was given, and y0 equals y naught, the initial point that was given. And then for n equals 0 to n minus 1, so we do n steps, I'm sorry, n minus 1 steps, I guess, going across, I'm sorry, n steps. For n steps, little n running from 0 to n minus 1. We select tn plus 1 is incremented by hn, the next step size, the next increment t, or delta tn if you like. Yn plus 1 is the current y plus, it's saying the length of the step times the slope of the line segment. That is the rise in y by a tangent line, right? If you go over hn, the rise in the tangent line is f prime, the slope of the tangent line, times the step you took, right? Slope times base, slope times run equals the rise, gives you the rise to this point. So that's what Eulers' method is doing with this step right here, is saying the next y value ought to be the run times the slope in the tangent line, gives you the rise in the tangent line. All right. The most important case is you choose each step size hn equal to constant h, which is b minus a over n, the length of your interval divided by the number of points. Let's try a simple example on here. Suppose I want to numerically estimate the points in the solution to this initial value problem. dy dt equals t plus y. Maybe I don't know how to solve that one. And also I need an initial value to use a numerical method, so I put y at 0 equals 1, and t equals 0, y equals 1. I use Euler method with 2 steps. I'll just do 2 steps. T going from 0 to 1. So I begin with t equals 0, the initial point of the interval, and y0 equal 1 because that's the initial value I'm given. Then t1, I just step by the step size, which I'm going to say is 1/2. T is going from 0 to 1 in 2 steps. Then the length of each step, h, is 1 minus 0 over 2. The length of the interval divided by 2 steps is 0.5. So I'll compute the step size, b minus a over n, n equals 2 steps. And I'll say the next value of t is 0 plus 1/2 is 1/2. Y, just by the Euler method, y1 is y0 plus the step size times the slope, f at t0, y0. Well, the function at t0, y0 is t plus y at t0, y0, so I take 1, the value of y, plus 0.5, the length of the step, times y0 plus t0, the initial value point, gives me 1.5. So I'm estimating that the next point in the solution curve is t equals 0.5, y equals 1.5. Now I'll take another step. I just keep repeating this. It's an algorithm, right? T2, I take another step of 0.5. I take T1, which is 0.5, and add h, which is 0.5. And I get to t equals 1. At t equals 1, I get y2 is y1 plus 1 times the slope, gives me the rise of the tangent line, is 0.5 times f is t plus y. So I take y1 plus h times t1 plus y1. The slope of the tangent line to the solution curve. And I get 1.5 from the last step plus step size of 0.5 times the slope of the tangent line, 0.5 plus 1.5, gives me 2.5. And what I've got is a table. Here's my step n. At step 0, I have the 0.01, my initial value. And the true solution is 1, because that was given me exactly. But I take one step, t goes to 0.5. I take two steps, t goes to 1. At 0.5, I estimated y is 1.5. The actual value, this is the solution of the differential equation, 2e to the t minus 1. And so at these values tn, I would get 1.797 if I really put in t equals 0.5. Instead, I got 1.5, that's close to it. I go another step, at t equals 1, I estimated y was 2.5 up here. The actual solution should be 3.437 if I would have plugged into the exact solution. So I'm starting to get further off, but the fact is, in Euler's method, if you choose your step size smaller, you'll get closer for any nice differential equation. So if I were to choose step size 0.25 instead of 0.5, I would be much closer to this value. If I choose step size 0.001 and take 100 steps, I would be very close to this. And the smaller the step size, the closer this tends to get to the real solution. This is what engineers have to do in practice when they've got complex aerodynamic equations. They can't solve them exactly. They go run to the computer and let some method, usually something more complicated than Euler's method. But the smaller the step size, even Euler's method will give you a good approximation usually. So this is Euler's numerical method to estimate solutions. Try some of the homework problems that are like this. They give you a differential equation with an initial value. They'll say, take so many steps, tends to be more like 10 steps. And they'll, you can calculate this with your hand calculator, calculate all these values, and you can compare them with the true solution often. There's also an error value. The errors are the difference between these two. I should move this over, I suppose. Let's see if I can close this out and get a little more room. The difference, this one minus this one, is 0.297. That's the error. The absolute value of this is called the absolute value, absolute error, and in this case it's the same because the error is positive anyway. So this is the absolute error between the true and the estimated solution by Euler's numerical method. You can also do what's called the relative error. If you divide this by the solution, this over 1.5 would be the relative error, and then if you multiply that by 100%, you get the percentage error. Here's what we can do if we get more steps. Suppose I want to solve this time dy dt equals minus 2y with the initial value y of 0 equals 4. So I start at step 0 with t equals 0 and y equals 4. The true solution is also 4. It was given. The error is nothing, right? If I take one step with h equal 0.1 this time, the estimated value by Euler's method, you can see it up here. y0 plus h times f of t0 y. Sorry, my computer, or my camera timed out. In each step, you increment t by the same amount, 1/10. Doesn't have to be the same, but for our examples, it will always be the same. And then you take y1 equals y0 plus h times f of t0 y0. y2 is y1 plus h of f times f of t1 y1. y3 is y2 plus h times f of t2 y2. And keep doing that. You are the machine. And you calculate these values, 3.2, 2.56, and then you get this one, and this one, and this one, this one. These are the values you get integrating in 10 steps from t equals 0 to t equals 1. This function, dy dt equals minus 2y. And Euler's method gets you initially pretty close, right? 3.2 to 3.27, 2.56 versus 2.68. But as you keep going on, it tends to get further. By taking the step size smaller, you would have gotten closer than this. Here's the list of errors. You just subtract these. If you take the absolute value, that's the absolute error. Euler's method has this property that for typical differential equations, if you take 10 times as many steps, you tend to reduce the final error by about a tenth. If you take 100 times as many steps, it tends to reduce the final error by a factor of 100 times as small, so you get about 2 more digits. That's not actually very good. Other methods that are more sophisticated from numerical methods class will do better. But try some of these homework problems similar to this and see if you can get them. Here's an example of that problem. Here's the true solution. If you took Euler's method with 10 steps like we did, here's, with n equals 3 steps first, you don't do very little. 1, 2, 3, and look how far the solution is off on that one. But if you took 5 steps, see how the green dotted lines are coming closer. Euler's method is just giving you these points. I'm just connecting them with dotted lines for visual purposes. The 10 steps we took is coming this close, and if you took 100 steps, you'd be much closer, and 1,000 steps much closer. As you can see, Euler's method eventually zips in on the solution if you keep using more steps.